Hi everyone, my name is Orko. Welcome to the group presentation of PG23. Reinforcement learning, first introduced by Shannon and Bartu, was incorporated with deep learning by Google's DeepMind paper in 2015, which gave rise to DQ. Since then, there have been a lot of such papers using deep Q networks. Over the years, quite a few issues have been identified. We look at 3 such papers which address these limitations in the study. The first paper addresses the issue of limited memory. DQNs are more suited for fully observable scenarios and have issues in partially observable scenarios. DQNs exhibit maximization bias and overestimation. This is addressed by paper 2 of the study, which discusses DDQNs, double DQ networks. DQNs suffer from a poor start issue, which is addressed by the paper deep learning from demonstrations. Next slide, please. The first paper, Deep Recurrent Q Learning for Partially Observable MTPs, addresses the first issue of limited memory of DQNs. DRQN is capable of overcoming the above problem. The authors propose model which introduces recurrency into the deep Q network using an LSTM. The authors claim that when trained with partial observations in Atari games, DRQN's performance is found to improve with incrementally more observations. On the contrary, when trained with full observations and evaluated with partial observation, DQRN's performance degrades less than DQN's. Here, the authors here have used convolution-based LSTM network to prove the efficacy of their proposal. So the game that the authors used in the paper was the Pong, and in the Pong game, they used to take snapshots of the images during the game, and that was the input to the model, which was passed through multiple convolution layers, 3 convolution layers to be specific, and then passed to an LSTM to extract features, and then passed to two fully connected networks to determine which action to be taken. There were 18 such actions in the Pong game, and hence the last layer is 18 nodes. Can I go to the next slide? So there are 2 types of ways to update a recurrent neural network. One of them is bootstrap sequential network and bootstrap random updates. In both the methods, episodes are selected randomly from the replay memory. For BSUs, the update starts at the beginning of each episode and is continued till the end of it. For BRUs, the update starts at random points in the episode and for only one backward call, and the hidden states of the RNN must be initialized to 0. BRUs adhere better to the random sampling experience, and to reduce the complexity is used by the authors. The DRQN implementation that we have made is slightly different from what the authors did. We have used a simpler version of the game. In this game, that to simulate this environment, we use the OpenAI Gym, the card pull game. In this game, the inputs are the card position, card velocity, pole angle, and the pole angular velocity. The pole angular velocity is not given to the paper, not given to the model as an input, in this case to simulate partial observability. And in case of the authors use a probability of p equal to 0.5 to simulate the partial observability, where each image was sent to a model, given as an input to a model. The inputs are passed through a LSTM followed by 2 fully connected layers to decide whether to go left or right. This the model that we use does not have any convolution layer, since it is since the features we do not need to generate features like the authors did from the images, and hence it can be directly fed to the LSTM. And please move to the next slide. So we mainly did 2 experiments for this paper. The first is in a fully observable scenario where the reward, as you can see, that the reward for the DQN and the DRQN are comparable, and in this as the authors claim, both of them have similar results. But if you move on to the next slide, in case of partially observable scenario, you would notice that the DRQNs perform quite better. They are constantly above the 200 range, while DQNs are not able to do so. And this proves that DRQNs do perform better in case of COM DPs, and it and our results also show that the claim the authors made that uh, that 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 every that in a fully observable scenario, DRQNs like in a fully observable scenario, DRQNs and DQNs perform better, and as observability goes down, reduces the performance of DQNs and DRQNs. DRQNs remains the same, but the performance of DQN goes down. DRQNs hence can be said to be more robust. For the next paper, moving on to Rishabh.
Thanks, Arka. Hi, guys. My name is Rishabh, and I have reviewed the deep reinforcement learning with double Q learning paper. Next slide. So when it comes to solving reinforcement learning problems, we have a few popular algorithms. One of them is Q learning. However, Q learning overestimates the action values for the states, leading to suboptimal policies and harms the performance of the agent. DQN is also a well-known algorithm that combines Q learning and neural networks and improves the performance of Q learning, but it also faces the same problems that Q learning face. To overcome these problems, we have double Q learning, which actually provides better performance than Q learning. So double Q learning uses different value functions to choose the greedy policy and to evaluate action values. So in this paper, we try to extend the concept of double Q learning to neural networks and expect an improvement in the performance. Next slide. So I'll be talking about Q learning, double Q learning, DQN, DDQN, and the performance of DQN and DDQN on Atari 2600 domain. And finally, I'll be mentioning my implementation and analysis of the performance of DQN and DDQN on cardpool environment. So next slide. So yeah. So to solve sequential decision problems, we can learn estimates for the optimal value of each action, defined as the estimated sum of future rewards when taking that action and following the optimal policy thereafter. An optimal policy is derived from actions with maximum values for each state. Next slide. Let's talk about Q learning and double Q learning. So the most interesting problems in reinforcement learning are too large to learn all the action values in all states separately. So in Q learning, we learn a parameterized value function to estimate the action values. Q learning is a form of temporal difference learning. And the interesting thing here is to notice the difference between the TD target of Q learning and double Q learning. While Q learning uses only a single value function to select the greedy policy and evaluate the action values, double Q learning uses separate value functions for the two tasks. Next slide. Yeah. So next we compare the overestimation of action values on different flexible and inflexible functions by Q learning and double Q learning. So the leftmost column shows the true values of the function in purple, and the estimated values of actions in each state by the green line. In the middle column, you can see that there is a dashed black line, which is the maximum estimated value. And in the rightmost column, we have the orange line, which represents the difference between the maximum estimated value and the true value. So we can clearly notice that this bias is much more than the estimate of double Q learning. So this way, the average error by Q learning is greater than the average error by double Q learning. Next slide. Yeah. So next next DDQN. So let's talk about DDQN. DDQN, as we know, combines Q learning and neural networks to evaluate action values. The performance of DQN is enhanced by the use of a target network and a replay buffer. However, DQN still faces the problem of over-optimistic action values that lead to suboptimal policies. This is because the max operator in DQN, as you can see in the equation, it uses the same values both to select and to evaluate an action. This makes it more likely to select overestimated values, resulting in over-optimistic value estimates. Next slide. So DDQN solves this problem by decoupling the two tasks. It uses an online network to select the greedy policy and uses the target network to evaluate the action values, as you can see in the equation. So next, we'll talk about the performance of DQN and DDQN on the Atari 2600 domain. As you can see in the table shows the summarized normalized performance on 49 Atari games. DDQN performs better with a huge margin. The plot shows the difference in the true value and overestimated action values by both DQN and DDQN on one of the Atari games. It can be clearly seen that DDQN overestimates the action values lesser than DQN. Next. So I evaluated the performance of DDQN and DQN on the cartpole environment. The criteria here to solve the environment is to get an average return greater than 195 for the last 10 episodes. And our hypothesis is that DDQN will perform better than DQN by reducing the overestimations of action values, and it will also lead to more stable learning. So as we can see, DDQN outperforms DQN by solving the environment faster. DQN takes around 24,000 steps to solve the environment, while DDQN does the same in 22,000 steps, which is a good difference to show the performance of DDQN and DQN. So next slide. We can also note that DDQN provides more stable learning. As you can see in the graph, as once the rewards are converging to 200 for both of them, DQN rewards take a dip at around 44,000 steps, whereas DDQN exhibits stable learning once converged. So this confirms our hypothesis that DDQN performs better than DQN, and it also leads to more stable learning. Thank you. Over to Sourav.
Thank you, Rishabh. Hi, everyone. I'm Sourav, and today we'll be focusing on DQFT, deep learning from demonstrations. So let's talk a bit about vanilla DQNs. So DQNs take time to learn good policies. In certain cases, up to millions of steps of performance will take place before the agent becomes well-trained. In a simulator-based environment, that's okay. But imagine if this is a real-world application, like a self-driving car. In this case, it's clearly not acceptable. So the graph below here illustrates this exact point here, where you can see poor performance for the first 40,000 or so steps before the reward function goes up to 200. In this case, this is on a cartpole environment where we kind of assume that the 200 is considered to be a fully working implementation, a fully trained example. So you can see that there is a poor performance here even up until the point where it gets fully trained. This is where DQFT comes in. So DQFT helps by getting a pre-trained agent. And it's an extension of the DQN algorithm where the model is pre-trained on data from a previous controller before entering the environment. So the previous control could be another agent, a human, basically anything that was controlling the system previously. The resulting output is that the system performs the task well straight from the start of training and continues to improve with its own self-generated data. So the couple of graphs you see over here are actually from the paper itself, implement two Atari games, Hero and Roadrunner. On the left, you see the game Hero. You can see that there is significantly improved performance on the DQFT graph as compared to the DQN graph. Adding to that, you can see the starting performance itself is significantly higher on the DQFT than in the DQN implementation. On the other hand, for Roadrunner, as the training iterations converge to 100 or so, 100, 200, the overall performance and the reward returns was about the same, but we can see clearly that for the first initial training steps, in less than 20 steps, we can see that DQFT had significantly higher rewards, which kind of alludes to the fact that DQFT does start with a model that is pre-trained as compared to standard vanilla DQN. So I'll be covering 6 key features of DQFT, starting with the pre-training, demonstration data prevalence, demonstration priority bonus, supervised losses, L2 regularization losses, and end-step temporal difference losses. So starting with pre-training. So DQFT initially pre-trains solely on the demonstration data before starting any interaction with the environment. During each iteration, the model samples B experiences from the demo data in the replay buffer and updates the network using gradient descent. So now this process repeats k times until the pre-training phase is completed. Note that in this state, the replay buffer only consists of demonstration data that is provided as part of the model itself. Now we move on to the actual phase when we actually work with self-generated data. In this case, what's important to note is that there's demonstration data prevalence. Here, what happens is that DQFT, the agent, once training is completed, the agent starts acting in the environment and collecting self-generated data. As you obtain more and more data, this data is added to replay buffer, replay in a FIFO-based schema. Now, at some point, this replay buffer becomes full, and there comes a decision where do we keep the demo data or the subdata data. In this case, what DQFT does, it keeps all the demo data and only keeps the most recent case subgenerated data points. In this case, once the subgenerated data fills the replay buffer, we discard the oldest point and replace it with the newest data point. And yeah, so this basically allows us to preserve the demo data at all times. Okay. The next thing is the demonstration priority bonus. So we like to give more priority on demonstration data simply because that is the data that is adjudged to be correct. So during the sampling process, during the training of the Q network, we have different constants that are added to the priorities of the agent and demonstration transitions. So this controls the relative sampling of the demo versus agent data and effectively boosts the frequency that the demonstration data is sampled over the self-generated data. This is because we consider demonstration data to be correct as compared to the self-generated data, which might have some error associated with it. The last thing we want to cover is the loss equation. The loss equation is comprised of 4 individual losses here. So the first one is the one-step double Q learning loss. Second is the n-step double Q learning loss. Third is supervised large margin classification loss. And the fourth is L2 regularization loss on the network weights and biases. So the one-step Q learning loss ensures that the network satisfies the Bellman equation and is the fundamental starting point of all temporal difference-based learning. Similar to the one-step Q learning, the n-step return loss uses the forward view. Using the forward view propagates the values of the expert trajectory to all earlier states, leading to better pre-training. The next thing is the large margin supervised loss. Now, this pushes the values of the agent's action to be at least a margin lower than that of the demonstration-based actions. This was again done to prioritize demonstration data over the self-generated data. This is actually similar to how we prioritize demonstration data that was shown a couple of slides ago when it comes to sampling. And lastly, the L2 regularization loss, this is fairly standard. We use this to prevent overfitting on the relatively small demonstration data set. Typically, the demonstration data set is orders of magnitude, 2 to 3 orders of magnitude smaller than the actual self-generated data, which is why we don't want to, we want to make sure that we don't overfit on the demonstration data itself. So as you can see, these 4 losses combined forms the fundamental backbone of the DQFT model. Now, the next thing we want to do is we want to go into the evaluation analysis of DQFT. So we evaluate on the corpus environment as in the previous 2 papers, and we compared with the vanilla DQN with a DQFT with human demonstrations. So this is the graph we see over here. And the first thing we note is that there's significantly improved results in early stage training. As you can see, within the first 100 steps itself, there's a clear difference in the performance of the 2 models. For DQFT, we take about 21 steps to cross the reward of 200, whereas in vanilla DQNs, we take 130 steps to cross 200 for the first time. The next thing is that there's markedly higher scores in the carpool environment. So the running average is roughly in excess of 400 for DQFT, whereas in DQN, the running average is maintained around 210 or so. Now, this is a big difference in the reward function, the reward scores that we get, and it's testament to how much more effective DQFT is, and the fact that the pre-training makes a massive difference in the model quality. Okay, so in summary, 3 main points I want to cover is that DQFT generates improved initial performance in real system using demonstration data as compared to vanilla DQNs. This is very obvious from the experimental data that we observed as well as what was demonstrated in the paper. The second key point is how DQFT is able to accelerate the learning process by combining supervised large margin classification loss and the traditional DQN losses as shown in the loss equation. And the last point is that DQFT incorporates demonstration data during post-training using prioritized experience replays, specific weights to improve the training process. And this allows it to basically accelerate the process and make sure that the training happens as quick as possible. So this ends our report on paper 3. And so to round things off, just have a quick conclusion to summarize everything that we have had so far. So as part of this project, we revised and implemented the code for DQN, DQRN, DDQN, and DQFD. And they've all shown that they improve on varied DQNs in different aspects. So we can see that in addition to these papers, there has been a multitude of other interesting works done in recent past, for instance, dueling DQN, rainbow agents, and which also try and improve on specific limitations of the original DQNs developed by Google in 2015. And so lots of interesting work there that we can look into the future. And this concludes our presentation. Okay, these are references, and we thank you for your time. Thank you.